So we just seen a few issues why that supervised training has. Some people may agree or not agree on this, and I must say that the supervised training, especially from the group of Jan LeCun, has produced some of the best results up to date. So when you have labeled data, you can really tailor a machine for a specific task, and it gives you great results. The question is, labeled data is very costly, and the training that is done on labeled data is also quite expensive computationally and in time. So let's look at other possibilities here. We will look first of all at unsupervised training techniques. One possibility of unsupervised training is basically to try to train a network at the same way as we did before, but this time we will not use a data set, so we will not have labeled data. We'll just have an image with something. So how can we really learn, how to train a network like this? So if I go back to the deep network architecture, so what we're gonna do instead, we don't really have a global signal about what this image that I presented is about, and we cannot really backpropagate the error. So what we can do is we can try to train one layer at a time to just to learn to extract some features from the image that that might be relevant and useful. So we'll work on a layer at a time, and we'll have an input image, we'll get an output, and somehow with this unsupervised technique we'll extract these filters. So the main idea really of unsupervised training is to do greedy training of one layer at a time. One popular technique was called autoencoders. So really one of the idea of autoencoders, the main idea that I want everyone who's listening to this lecture to take home is this. Main idea is that since you don't have a label, why don't we try to learn to reconstruct the input with some sparse space function. What it means is identified in this image here. So if this is the input image, what I want is I want to extract some filters that allow me to reconstruct the input image. So allow me to, they have to be sparse first of all. I don't want a lot of filters. I want to be parsimonious about, because having more of these filters will take more time to compute and make the network slow and so forth. So I want as few filters as possible that allow me to extract basically the main portions, the base function of this image, create an output, and I want the error between these two images to be as small as possible. So let's look at this diagram now here, now that I explain it on the figure. So you have an input image, so this one. You have an encoder. The encoder is basically you try to use some base functions, so you try to figure out some filters that encode this data into a list of other of base function and their positions, and you want to force it to have a sparsity constraint, so you want as little filters as possible. And you're gonna get a code here. This is the code that you get. Then you go into a decoder. The decoder basically takes this image, takes the code basically in the position and so forth, and reconstructs an image. So reconstructs this image in this output image. Now you take the input image and the output image, so these two, and you look at the error between the two, and you want it to be small. So you want these images to be similar, like in this case. I'm taking these slides an example from a paper from the following author from Jan LeCun's lab. But basically the main idea is, since we don't have a global signal that tells us what to do, we are going to try to encode the image with some base functions reconstruct it with those base function. So that's sort of like related to compression if you think about it. And I want this image to be as close as possible to the input. That's really the main idea about unsupervised training and autoencoders and so forth. Notice that even in this example, beside a strange feature that looks like an eye, most of the features that are learned are basically small patches of filters that look like a Bohr filter. They look like the same kind of filter that are implemented in V1 in our visual system, and the same kind of filters that you also get if you train a large supervised network. Notice also that this image is composed by just by these few features. So for example, there's a vertical filters which is used here, an horizontal filter that is used here. There's 45 degrees, 135 degrees, and in this case there's an eye because just the eye was fitting in the filter space, and that was like very optimal encoding. Notice that a lot of the air and other features don't get encoded because they look like noise and they don't have a lot of errors when they're reconstructed. So this is really the main idea about autoencoders. So what you do basically is you have the data set is just unlabeled data of any form. So these are like pieces of images, for example, images of backgrounds or images of faces that are being contrast normalized. And you try to find the base function or the basic building blocks that you can use to encode this image. So if you look at the at these algorithms in real time, basically what it does is at each iteration it tries to learn more and more of this base function. So as you can see, this is a moving GIF representation of this that doesn't play in a static moving frame like I'm trying to do. So really you have just unlabeled data of any form, video frames or everything, which is easy to get and easy to consume. And you learn this base function that sort of encode it in the best way. Other few important things about unsupervised training and autoencoders is that they are related to an engineering concept called vector quantization. So really you are trying to learn the base function of the input signal so that you can optimally reconstruct. And they're also used for compression and denoising. So as you can see in these examples here, you denoise the area that might have some noise, and you also compress the signal because now instead of encoding every pixel in here, you only have to encode these few base functions plus where they should be in the image. But this is really like compression algorithms are what compression algorithms really do.